Hello, welcome to a video about heat transfer. In this video we'll specifically be looking at conduction, but heat transfer can also occur via convection and radiation, and we'll look at these in later videos. So heat transfer can occur through conduction, convection and radiation, as I just said. In stage 1 physics, you'll need to be able to explain how heat transfer can occur through conduction, convection and radiation. You'll also need to be able to describe examples of each heat transfer. So just focusing on conduction for today. Thermal conduction is heat transfer that occurs via movement and collisions of particles within a material or object. So for example, in our situation here, we've got a Bunsen burner heating a metal rod. So in this situation, heat is transferred from the flame to the metal. And this increases the thermal energy of atoms and free moving electrons. So I'm going to write atoms and electrons here. So these electrons are delocalized because they're in metal. Translational kinetic energy of the delocalized electrons causes them to spread out and transfer heat through the metal bar. So EK and then trans of electrons, delocalized electrons, causes them to spread and transfer heat. Take notes on your handout as you're watching this. And this transfer occurs throughout the metal bar. The other form of energy transfer that's occurring is vibrational kinetic energy, and that's of the atoms close to the flame. And this is transferred via collision to neighbouring atoms within the metal rod. So that kind of explanation is what you'll need to be able to offer for these kind of processes. What we'll look at next is thermal conductivity, and this is the rate at which heat is transferred via conduction, and this is dependent on the material. With metals, they've got an increased thermal conductivity or a higher thermal conductivity, and this is because of their delocalized electrons. For non-metals, thermal conductivity is less or reduced, and this is because there's no free moving particles to transfer thermal energy via conduction. Thermal conductivity is measured in watts per meter Kelvin, so this is the unit for thermal conductivity. And in our table here, for example, we can see that steel has a value or a conductivity of 60 watts per meter Kelvin, as opposed to wood, which has a thermal conductivity of 0.15 watts per meter Kelvin. So this is why steel feels a lot colder to touch, because it has a higher thermal conductivity than wood. If you're touching it, the heat flows away from your hand faster or at a faster rate with steel than it does with wood. So that's why steel feels colder, and metals in general feel colder than non-metals. Continuing with thermal conductivity, we're going to consider it with different states of matter. Thermal conductivity is much greater in solids, and this is because The vibrational kinetic energy is transmitted much more rapidly through collisions because particles are situated closely together. These collisions that occur in solids don't occur frequently enough in liquids or gases to allow for efficient thermal energy transfer. So, for example, if you've got a match head next to a candle or a Bunsen burner, the match will only ignite when sufficient heat is transferred via conduction. But if it's too far away, the match won't ignite because air is a poor thermal conductor, so the heat doesn't transfer fast enough. Gonna watch a video now. Hopefully it works smoothly on the iPad. If it doesn't, then I'll just throw in a link and you can pause and go and have a watch, but we shall see. It worked last time I did this, so I'm feeling optimistic. Okay, it doesn't seem to be having a bar of it, so I'll just edit this video to include the video from YouTube. The music in the video really sucks. It's really like chipper and upbeat, and it's just shocking, so feel free to mute while you're watching. So that video there hopefully demonstrates the poor conductivity of water. What was happening was that an ice cube was kept in the bottom of the test tube with some netting, because usually ice will want to float to the top of water because ice is less dense than water. A Bunsen burner was boiling or heating the top section of water of the in the test tube, but by the time the water was boiling at the top, the ice was still fairly intact at the bottom. So this demonstrates that within the same vessel of water, you can have frozen water and boiling water. So water itself must be a relatively poor conductor of heat. The last bit that we'll look at is thermal insulators. So these are materials with low thermal conductivity, and this is because the rate of heat transfer is lower, and this therefore minimises the rate of heat loss. So you'll just need to be able to explain how these thermal insulators work, or like the process that is happening for them to work, or the process that isn't happening. So for example, with styrofoam or polyurethane, this is installed in roofs and walls, and this is because it minimises the rate at which heat transfer occurs via conduction from the interior to exterior. So these materials have low thermal conductivity. It's similar with wool. Wool is composed of long protein fibres, and these fibres trap air molecules or trap air, pockets of air into the material. And we know from a couple of slides ago that air is a good thermal insulator. So because wool is trapping these little pockets of air, and air is a good thermal insulator, this minimises the rate of heat transfer from the body to the surrounding air temperature if their surrounding air temperature is low.